November 16th, 1941. Mediterranean Sea off Gibraltar. HMS Marigold cuts through black water, her deck crew invisible in the moonless night. Lieutenant Commander Arthur Callaway stands in the wheelhouse, eyes straining uselessly into darkness that swallows everything beyond 50 yards. Somewhere ahead, U-433 prowls on the surface, diesel engines charging batteries while her commander believes the night makes his submarine invisible. Contact bearing 090, range 3,000 yards. The voice crackles through Marigold's intercom from the radar hut, a wooden box bolted to the superstructure that houses equipment so new that most Royal Navy officers don't trust it. The Type 271 radar, operating on 10-centimeter wavelengths that seem like science fiction to sailors trained on visual spotting and acoustic detection. Callaway's hand moves to the engine telegraph before his mind fully processes what he's hearing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The radar operator isn't guessing. He's reading electronic blips on a cathode ray screen, tracking a submarine that has no idea it's been detected. In 3 minutes, either Marigold will close to depth charge range, or the U-boat will dive and vanish into Mediterranean depths, where only sonar can follow. All ahead, full. Come left to 090. Prepare depth charges. The corvette surges forward, her single screw churning white phosphorescence that trails behind like a comet tail. Below decks, the crew scrambles to action stations, loading 300-pound depth charges onto stern racks while gunners train their 20mm Oerlikons into the darkness ahead, ready to fire at whatever target emerges from the night. Range 2,000 yards. Target maintaining course and speed. Still surfaced, sir. The radar operator's voice carries the excitement of watching technology work exactly as promised, revealing what human eyes cannot see, tracking what ears cannot hear, making the invisible visible through nothing more exotic than reflected radio waves. For 18 months, German U-boats have owned the night, surfacing after dark to charge batteries and maneuver into attack positions, while Allied escorts blundered blindly through darkness, depending on lookouts whose eyes couldn't penetrate beyond a few hundred yards in good conditions and almost nothing in heavy weather. 70% of successful U-boat attacks happen at night on the surface, exploiting the fundamental limitation that ASDIC sonar can only detect submerged submarines, while conventional radar sets are too large and too crude to pick up anything as small as a submarine's conning tower. Until now, range 1,000 yards. Target beginning emergency dive, sir. Callaway can picture it clearly even though he still can't see the submarine. The U-boat commander has finally spotted Marigold's silhouette against the slightly lighter horizon. Or perhaps he's heard the corvettes, engines closing at full speed. The sudden scramble on deck as the watch crew drops through the conning tower hatch, the dive klaxon screaming its two-toned warning, the ballast tanks flooding as the submarine tilts bow down into the safety of depth. Standby depth charges. Pattern Baker 7. Set for 150 feet. The U-boat has perhaps 45 seconds head start, time enough to reach 50 or 60 feet if her commander is skilled and her crew well drilled. But Marigold knows exactly where the submarine dove, tracked by radar right up to the moment the conning tower disappeared beneath the surface. No more blind, dropping over the stern. No more hoping that calculations of speed and heading are accurate enough to place 300 pounds of TNT close enough to crack a pressure hull. Fire depth charges. The heavy cylinders tumble from the stern racks, their clockwork fuses counting down the seconds until detonation at preset depths. Marigold's wake churns white as the charges disappear into black water, each one searching for the submarine that dove 15 seconds too late. The explosions come in rapid succession, massive columns of water erupting behind the corvette as the TNT detonates at depth. The concussions hammer through Marigold's hull, rattling equipment and throwing sailors against bulkheads. For 30 seconds, the sea boils with acoustic chaos. When the water clears, debris floats to the surface, oil, wood fragments. The unmistakable evidence that U-433 will never return to her French base. The first confirmed kill by Type 271 radar. Proof that a civilian invention developed in a laboratory 600 miles away has just changed the fundamental mathematics of submarine warfare. What the Royal Navy's own experts said was impossible, what traditional naval officers dismissed as an unproven toy, has just killed a German submarine in total darkness, using nothing more than reflected radio waves and a cathode ray tube. 600 miles north in Portsmouth, England, a team of scientists and engineers who never wore naval uniforms are about to learn that their impossible idea works. That radar, small enough to fit on a corvette, operating on wavelengths short enough to detect a conning tower, can do what centuries of naval tradition said could never be done. Make submarines visible in the dark. September 1940, London. The Trade Protection meeting convened in a windowless conference room at the Admiralty Building with the grim urgency of men watching Britain slowly starve. The statistics were brutal and undeniable. Monthly merchant ship losses had climbed to 300,000 tons. U-boats were sinking vessels faster than British shipyards could replace them. Food imports had dropped to levels that threatened civilian morale, and 70% of successful submarine attacks happened at night on the surface, when German commanders surfaced their boats to charge batteries and maneuver freely, confident that darkness made them effectively invisible. Admiral Sir Dudley Pound, First Sea Lord, studied the tactical reports with the methodical precision of a career naval officer, analysing a problem that threatened to lose the war before American entry could tip the balance. The numbers told a story that traditional naval doctrine couldn't answer. ASDIC sonar worked brilliantly against submerged submarines. Depth charges could destroy any U-boat they could locate, but surfaced submarines at night were essentially undetectable. Lookouts strained their eyes into darkness that revealed nothing beyond a few hundred yards. The radar sets available in 1940, operating on metre-and-a-half wavelengths, were too crude to detect anything as small as a submarine's conning tower. The Type 286 radar could track large surface ships and aircraft, but its long wavelength and massive antenna made it useless for anti-submarine work on small escort vessels. We need an efficient radar set for anti-submarine surface and air escorts, Pound declared, his voice carrying the weight of someone stating an impossible requirement. Something that can detect a surfaced submarine at ranges useful for attack, something small enough to fit on corvettes and frigates, something that works at night in heavy weather when visual spotting fails completely. The assembled officers shifted uncomfortably. Traditional naval thinking said such a radar was impossible. The laws of physics required short wavelengths to detect small objects, which meant high frequencies that demanded sophisticated electronics nobody had successfully miniaturized. The antenna alone would need to be small enough for a corvette's superstructure, while maintaining enough directional precision to distinguish a submarine from wave clutter. And it needed to work reliably in salt spray and North Atlantic storms, conditions that destroyed most electronic equipment within weeks. This requirement has highest national priority, Pound continued. Prime Minister's orders. Whatever resources are needed, whatever experts must be recruited, this radar will be developed, because if we can't stop U-boats from owning the night, we'll lose this war before Christmas 1941. 40 miles southwest in Swanage, at the Telecommunications Research Establishment, a small team of civilian scientists was already working on the impossible. Dr. Edward Bowen and his colleagues at the Radar Research Laboratory had spent the previous year developing airborne interception radar for night fighters. Their work with the cavity magnetron, a device that generated high-power microwave frequencies, had opened possibilities that seemed like science fiction to anyone trained in traditional radio engineering. The cavity magnetron wasn't elegant. It was a chunk of copper with precisely machined holes, cooled by forced air and powered by high voltage that could kill a careless technician, but generated 10 kilowatts of power at 10-centimeter wavelengths, frequencies high enough to detect objects as small as a person and precise enough to track them with startling accuracy. What if we adapted the cavity magnetron for surface search? Bowen suggested during a November 1940 meeting with naval representatives. 10-centimeter wavelength, directional antenna, small enough to mount on a corvette's bridge. The naval officers listened with the skepticism of professionals who had heard promising ideas fail when exposed to seawater and combat conditions. "Can it detect a submarine at useful range?" Captain B. R. Willett asked. "Define useful." 3,000 yards, Willett replied. "Long enough for a corvette to close to depth charge range before the U-boat commander realizes he's been spotted. At night. In rough seas. With salt spray covering the antenna." Bowen considered the requirements with the careful precision of a scientist who understood the difference between laboratory demonstrations and operational weapons. "The cavity magnetron generates enough power. The wavelength is short enough to detect a conning tower. The challenge is packaging it for shipboard use and making it reliable enough that crews will trust it. We'll need perhaps 6 months of development. Testing on actual submarines, refinement of the antenna design, and we'll need cooperation from your engineers, because we're civilians who've never set foot on a warship." "Build us a demonstration unit," Willett said. "Something we can test against real submarines. If it works as promised, you'll have every resource the Royal Navy can provide." On November 11th, 1940, the test took place in waters off the English coast. HMS Usk, a British submarine, volunteered as the target, running on the surface at various ranges, while Bowen's experimental radar tracked her from a fixed installation on shore. The results exceeded even optimistic predictions. 7 miles. The radar detected the submarine at 7 miles in calm seas, tracking her with enough precision to plot course and speed. When Usk dove and ran submerged with only her periscope showing, the radar still maintained contact at shorter range. This wasn't marginal performance. This was revolutionary capability that could transform anti-submarine warfare if it could be engineered into a system small enough to fit on escort vessels. "We need this on corvettes," Willett declared after reviewing the test results. 1,000 units if you can manufacture them, every escort in the fleet. This is the weapon that will win the Battle of the Atlantic. In October 1940, a team from the Admiralty Signal Establishment under Stenhard Landale arrived at Swanage to study Bowen's experimental radar and begin the brutal work of transforming laboratory equipment into operational weapons. What worked perfectly in controlled conditions needed to survive North Atlantic storms: salt spray that corroded, electronics within days, the violent motion of small ships pitching through heavy seas, and the mechanical stress of depth charge explosions that could shake equipment loose from mounting brackets. The antenna proved the most challenging component. Early radar sets used massive arrays of dipoles, antenna elements that required precise spacing to maintain the directional beam needed for accurate tracking. Such antennas were far too large for corvettes and frigates, where every square foot of superstructure was needed for weapons and crew spaces. The solution came from an unexpected source: ECS. Megar and his team at GEC Research Laboratories had been developing a different type of antenna for coastal defense radar, the cylindrical paraboloid, mockingly called a cheese antenna because its cross-section resembled a wheel of cheese sliced in half. The design used a curved reflector to focus radio waves into a narrow beam, achieving directional precision with an antenna small enough to mount on a corvette's bridge. The cheese antenna became the foundation for what would eventually be designated Type 271 radar, a cylindrical paraboloid mounted in a transparent perspex housing, manually rotated by an operator using a simple steering wheel connected to a shaft passing through the roof. The entire assembly was compact enough to fit atop a corvette's bridge house, requiring no more space than a large searchlight. By December 1940, a breadboard prototype was tracking submarines at 13 miles range in calm seas. The combination of cavity magnetron, cheese antenna, and microwave receiver worked exactly as theory predicted. Radio waves at 10-centimeter wavelengths bounced off a submarine's steel hull with enough energy to create a visible blip on the cathode ray tube display. The operator could measure range by reading the position of the blip on the scope. Direction came from the antenna's pointing angle. Together, these two pieces of information gave ships the ability to track submarines with precision impossible through visual observation. But prototype performance in controlled conditions meant nothing until the system worked in combat. The equipment had to survive the mechanical violence of storm conditions, maintain calibration through temperature swings from below freezing to tropical heat, resist corrosion from salt spray that penetrated every seal and gasket, and operate reliably when maintained by exhausted sailors who were not electronics engineers. Engineering challenges that looked trivial on paper proved nightmarish in practice. The early cavity magnetrons failed after a few hundred hours of operation. The cathode ray tubes cracked when subjected to the vibration of depth charge attacks. The rotary joint that allowed the antenna to sweep through 360 degrees while maintaining electrical connection to the transmitter below leaked seawater, shorting out the electronics. Each problem required its own engineering solution, tested and refined through iteration that consumed months of work. The transmit-receive switch proved particularly difficult. The cavity magnetron generated such high power that it would destroy the sensitive receiver if both tried to use the same antenna simultaneously. Engineers at the Clarendon Laboratory at Oxford University developed the TR switch, a device that automatically disconnected the receiver during transmission pulses, then reconnected it milliseconds later to catch the returning echo. The mechanism worked through clever use of gas-filled tubes that became conductive when exposed to the high-power transmitter pulse, shorting the receiver circuit to ground. When transmission ended, the tubes returned to their non-conductive state, allowing the weak echo signal to reach the receiver. It was elegant engineering that solved an impossible problem, making practical radar possible on a single antenna. By March 1941, the first production, the unit was ready for sea trials. HMS Orchis, a newly completed Flower-class corvette, was set aside for testing. The Type 271 radar was mounted atop her bridge at a height of 36 feet, giving the radar an unobstructed view of the surrounding sea. The installation required 3 days of work, running coaxial cables from the antenna down to the receiver and display unit in the operator's cabin directly below, installing the power supplies and transmitter in a cramped equipment room, training the crew on operation and basic maintenance. On March 25th, Orchis steamed into the Firth of Clyde for operational trials that would determine whether 6 months of desperate engineering work had produced a weapon or an expensive failure. The test submarine was running on the surface 4,000 yards away, her conning tower barely visible as a dark shape against the slightly lighter horizon. In Orchis's radar cabin, Petty Officer Thomas Brennan watched the cathode ray display with the intense focus of someone whose report would determine whether the Royal Navy ordered 1,000 radar sets or abandoned the entire program. Range 4,000 yards, Brennan reported, his voice neutral despite the excitement of watching technology work exactly as designed. Bearing 090, target maintaining steady course and speed. On the bridge, Lieutenant Commander James Harrison confirmed the radar's accuracy by visual bearing, though the submarine was barely visible in the dawn light. Matches visual perfectly, he noted in the log. Radar is tracking the target with precision I've never seen from any electronic system. For the next 6 hours, Orchis ran repeated approaches on the test submarine, while Brennan tracked her from ranges varying from 5,000 yards down to a few hundred. The radar worked flawlessly, maintaining contact even when the submarine executed evasive maneuvers, tracking her through turns and speed changes with enough precision to provide accurate firing solutions for depth charge attacks. In higher sea states, maximum range dropped to about 4,400 yards as wave clutter began masking the submarine's echo. But even this reduced performance vastly exceeded visual observation capability at night or in poor weather. After successful testing, the prototype was declared operational in May 1941 and orders were placed for mass production. By September, 32 corvettes had been equipped with Type 271 radar. The Royal Navy finally possessed the ability to detect surfaced submarines at night, tracking them through the darkness that had previously provided perfect concealment. But operational success required more than working equipment. It required crews who understood how to use the new technology, tactics that exploited radar's capabilities while acknowledging its limitations, and commanders willing to trust electronic blips over centuries of visual observation tradition. The learning curve proved steeper than anyone anticipated. HMS Marigold's successful attack on U-433 in November 1941 demonstrated what radar could accomplish in ideal conditions. A surfaced submarine on a calm night, detected at 3,000 yards, tracked during her emergency dive, destroyed by precisely placed depth charges. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But combat rarely offered ideal conditions. North Atlantic convoys faced storms that created wave clutter, masking submarine echoes, equipment failures from salt spray corrosion, and the psychological challenge of trusting technology that seemed like magic to sailors trained in visual observation. Lieutenant Commander Arthur Callaway spent the months after his first radar kill training other corvette commanders in tactics that exploited the new capability. The key insight was patience. Radar allowed ships to track submarines from ranges far beyond visual observation, but closing to attack range required careful approach to avoid alerting the U-boat commander. Maintain contact at maximum range, Callaway explained during a training session at Liverpool in December 1941. Plot the submarine's course and speed. Plan your approach to close from behind or from a blind angle. When you're 1,500 yards away, the U-boat commander might spot your silhouette. That gives you perhaps 90 seconds before he dives. Use them wisely. The tactical revolution extended beyond simple detection. Radar-equipped escorts could coordinate attacks with unprecedented precision. One ship maintained contact while directing others to optimal attack positions. When submarines dove to escape, the tracking ship knew exactly where they submerged, eliminating the geometric guesswork that plagued conventional depth charge attacks. By early 1942, the statistical evidence was becoming undeniable. Radar-equipped escorts were achieving submarine kills at rates 3 to 4 times higher than ships, relying on visual observation alone. But the technology brought unexpected challenges. The early Type 271 systems required constant maintenance by crews who were not electronics technicians. The cathode ray tubes failed unpredictably, leaving ships blind at critical moments. The cavity magnetrons needed replacement every few hundred hours of operation, and spare parts were chronically scarce. Salt spray corroded connections faster than anyone predicted, requiring daily cleaning and inspection to maintain reliability. Most frustrating was the radar's inability to distinguish between submarines and other objects. Whales produced echoes similar to U-boats. Heavy wave action created false targets. Fishing vessels and debris fooled inexperienced operators into wasting depth charges on phantom contacts. Petty Officer Brennan, now training radar operators at the Liverpool base, developed recognition techniques that separated real submarines from false echoes. A whale's movement is erratic, he explained, pointing to the characteristic pattern on the display screen. Surfaced submarines maintain steady course and speed. When you track a contact for 5 minutes, the pattern tells you what you're seeing. Trust the mathematics, not your assumptions. By mid-1942, 236 Allied ships carried Type 271 or its variants. The radar had evolved through multiple improvements as engineers refined the electronics and operators provided feedback from combat experience. The Type 271Q, introduced in 1943, used a 100-kilowatt magnetron compared to the original's 5 kilowatts, dramatically increasing detection range. More importantly, the Q model incorporated the plan position indicator display that revolutionized radar operation. Instead of watching blips on an A-scope that showed only range and required careful antenna positioning to determine bearing, operators now saw a circular display where contacts appeared as bright spots at their actual relative positions. The PPI display, what everyone now thinks of as a radar screen, transformed submarine hunting from a technical exercise into an intuitive process. Operators could see at a glance where submarines were located relative to their own ship, plot intercept courses directly on the display, and coordinate multiple ships with precision impossible through voice communication alone. But as Allied radar capability improved, German countermeasures evolved to match it. In August 1942, U-boats began carrying a simple device that would temporarily neutralize the radar advantage. Allied escorts had fought so hard to achieve. The METOX detector was elegantly simple, a basic radio receiver tuned to detect the 1.5-meter wavelength used by early Allied radar systems. When Allied aircraft or ships activated their radar, the METOX receiver picked up the transmission long before the radar could detect the WWII submarine, giving U-boat commanders minutes of warning to dive to safety. The device was manufactured in France by METOX Grandin, giving it the code name that Allied intelligence would spend months trying to understand. Within weeks of METOX deployment, U-boat detection rates plummeted. Submarines that had been reliably tracked at night now vanished as soon as radar pulses reached them, diving to safety, while Allied escorts searched empty water. Captain Lieutenant Hans Rudolf Rösing's war diary from September 1942 recorded the tactical revolution from the German perspective. The detection device gives us perhaps 4 minutes warning before enemy aircraft arrive, he wrote. Sufficient time to dive and escape even when caught on the surface charging batteries. Whatever technology the British are using, we can now detect it before it detects us. The advantage has shifted back to the hunter. Admiral Karl Dönitz, commanding the U-boat fleet from headquarters in Paris, recognized immediately that METOX had restored the tactical balance. U-boats could again operate on the surface at night, with reasonable confidence, surfacing to charge batteries and maneuver into attack positions, while Allied radar revealed its presence through transmissions the submarines could detect. Monthly merchant ship losses climbed back toward 300,000 tons as the German submarines exploited their new technological advantage. In London, the Admiralty convened another emergency meeting in October 1942. The statistics told a grim story. Radar-equipped escorts had achieved 3 months of success from May through July, driving monthly losses down to manageable levels. Then, METOX deployment reversed those gains, returning the Battle of the Atlantic to the desperate mathematics of submarines sinking ships faster than Allied shipyards could replace them. "We're being detected," declared Captain Willett, reviewing intelligence reports from interrogated U-boat prisoners. "The Germans have some kind of receiver that picks up our radar transmissions. They're diving before we can close to attack range. Every radar pulse we send out tells them exactly where we are." The solution was already under development, though few people outside the telecommunications research establishment knew about it. ASV Mark III, the airborne version of Type 271 radar operating on 10-centimeter wavelengths that METOX couldn't detect. German radar detector development had focused on meter wavelength systems because that's what Allied radar used in 1941. The massive leap to microwave frequencies caught them completely unprepared. Their receivers couldn't detect 10-centimeter transmissions, meaning Allied radar was once again invisible to submarine crews. The first operational test came on March 1, 1943, when a Royal Air Force Wellington equipped with ASV Mark III detected a U-boat running on the surface in the Bay of Biscay. The submarine's METOX receiver remained silent because it couldn't detect the microwave radar. The Wellington closed to attack range before the U-boat commander realized he'd been spotted, dropping depth charges that damaged the submarine severely enough to force her back to base. Within days, similar attacks convinced German naval intelligence that Allied forces had deployed a new radar operating on wavelengths their detection equipment couldn't monitor. "The British have changed to a different wavelength," Dönitz noted in his war diary on March 7, 1943. "Our detection equipment is useless. The boats are being surprised on the surface without warning. This represents a critical threat to submarine operations." German technical intelligence scrambled to understand the new radar, but microwave technology remained beyond their engineering capability in early 1943. They had neither the cavity magnetrons to generate high power at short wavelengths, nor the crystal detectors to receive the weak echoes. British and American scientists had a 2-year head start in microwave electronics, a lead that would prove decisive in the technology race that determined control of the Atlantic. By mid-1943, the combination of Type 271 surface radar and ASV Mark III airborne radar created an environment where U-boats could no longer operate safely on the surface at any time of day or night. Detection ranges extended to 5 miles or more in good conditions. Submarines caught on the surface faced immediate attack before they could dive to safety. The psychological impact on U-boat crews proved as devastating as the physical threat. Oberleutnant Werner Hartenstein described the new reality in a letter to his family in April 1943, recovered after his boat was sunk. "We can no longer trust the darkness. Aircraft appear without warning, as if guided by some invisible hand. Our detection equipment shows nothing, then suddenly searchlights illuminate the boat and depth charges explode around us. The crew's nerves are shattered. Every man knows that surfacing to charge batteries might be the last thing we do." The strategic balance had shifted decisively. German submarine construction continued at high rates, launching new U-boats faster than Allied escorts could sink them. But operational effectiveness collapsed. Boats that once patrolled the Atlantic for months returned to base after weeks, their batteries exhausted, and their commanders reporting that they could no longer surface safely to recharge. Monthly merchant ship losses dropped from 300,000 tons to 150,000, then to less than 100,000 by late 1943. The Battle of the Atlantic, which had threatened to starve Britain into surrender, was being won through technological superiority as much as industrial production. Lieutenant Commander Callaway's patrol report from June 1943 captured the transformation in cold statistics. 7 submarine contacts in 9 days. 5 confirmed kills. No merchant ships lost. The Type 271Q radar detected all contacts at ranges exceeding 4,000 yards. Attacks were coordinated with HMS Vetch and HMS Rhododendron, using radar tracking to position ships for optimal depth charge patterns. The Germans no longer own the night. We do. The tactical lessons learned from 18 months of radar operations had matured into doctrine that maximized the technology's advantages. Escorts maintained continuous radar watch while approaching convoys from behind, where submarine lookouts would be focused forward toward the merchant ships. Once contact was established, the tracking ship directed other escorts to approach from different angles, creating a coordinated attack that prevented submarines from evading in any direction. When U-boats dove, the precise knowledge of where they submerged allowed depth charge attacks with unprecedented accuracy. But the technology's greatest contribution might have been psychological rather than tactical. German submarine commanders lost confidence in their ability to operate on the surface, even at night. The darkness that had once protected them now felt like a trap, where invisible detection could come from any direction without warning. The aggressive tactics that characterized German submarine warfare in 1940 through 1941 gave way to caution born from repeated surprise attacks that seemed to violate the laws of nature. "How can they see us in total darkness?" Kapitänleutnant Peter Kremer demanded after surviving a night surface attack in July 1943. There was no moon, no searchlights, no illumination of any kind. Then, suddenly, depth charges exploding all around us. Some new weapon, something we don't understand and can't defend against. The answer, of course, was radar operating on wavelengths German technology couldn't match. By August 1943, German naval intelligence had captured enough Allied equipment to understand the basic principles. The British are using 10-centimeter radar generated by some kind of advanced electronic tube, a technical intelligence report concluded. Our attempts to duplicate this technology have failed. We lack both the manufacturing capability to produce such tubes and the receiver technology to detect their transmissions. Recommendation is to abandon surface operations in areas of known Allied radar coverage. This was tantamount to admitting defeat in the Atlantic, since Allied radar coverage now extended across most of the ocean. The German response came in 2 forms, neither particularly effective. First, they developed the Naxos radar detector, which could detect 10-centimeter transmissions but only at very short range. By the time Naxos warned of radar, Allied aircraft or ships were already close enough for visual detection. Second, they introduced the schnorkel, a breathing tube that allowed submarines to run their diesel engines while remaining submerged, eliminating the need to surface for battery charging. The schnorkel solved the charging problem but created new vulnerabilities. The tube extended above the surface, creating a radar target that Type 271 could detect at ranges approaching 5,000 yards in calm seas. The submarine remained submerged, but escorts now knew exactly where to drop depth charges. And schnorkel operations reduced submarine speed to a crawl, making it nearly impossible to pursue fast-moving convoys or escape when detected. The technology that was supposed to restore German submarine effectiveness actually made boats easier to find and harder to maneuver. The final statistics told the story with mathematical precision. In 1940, before Type 271 radar deployment, German U-boats sank over 1,000 merchant ships, totaling more than 4 million tons. In 1941, as radar began deployment but remained uncommon, losses remained above 3 million tons. In 1942, with radar becoming widespread, losses dropped to slightly over 2 million tons. In 1943, with microwave radar achieving full operational capability, merchant ship losses fell to 1.4 million tons, despite Germany deploying more submarines than ever before. The trend continued through 1944, when Allied merchant ship losses dropped below 800,000 tons, while German submarine losses climbed to over 200 boats destroyed. The Battle of the Atlantic had been decisively won, not through any single weapon or tactic, but through the systematic application of technological advantages that German engineering couldn't match. Type 271 radar, operating on 10-centimeter wavelengths that seemed like magic to sailors trained in visual observation, had made submarines visible in total darkness. Combined with improved sonar, forward-firing hedgehog weapons, better depth charges, escort carriers providing air cover, and the breaking of German naval codes, radar transformed submarine hunting from a desperate gamble into systematic destruction. Charles Callaway received the Distinguished Service Cross in November 1943 for his role in developing radar tactics and achieving 7 confirmed submarine kills. The citation praised his exceptional skill in anti-submarine operations, but made no mention of radar, which remained classified technology. He spent the ceremony thinking about the young radar operator aboard Marigold, who had first detected U-433 in November 1941, tracking the submarine with technology so new that neither of them fully trusted it. That single detection, that first confirmed kill, had validated 6 months of desperate engineering work and proved that civilian scientists who never served aboard warships could create weapons that traditional naval officers hadn't imagined. By 1945, as the war in Europe ended, Type 271 radar had been installed on over 1,000 Allied vessels. The microwave technology developed for submarine detection had spawned a revolution in electronics that would continue long after the war. Cavity magnetrons became the heart of microwave ovens. Radar evolved into air traffic control, weather tracking, automotive collision avoidance, and 100 other applications that made reflected radio waves part of daily life. But in the cramped radar cabins of corvettes and frigates battling Atlantic storms, the technology meant something more immediate and practical. It meant the ability to find submarines in total darkness, to track them through evasive maneuvers, to kill them before they could kill merchant sailors. The German submarine force, which had brought Britain to the edge of defeat in 1941, became hunted prey by 1943. U-boat commanders who once attacked with confidence learned to fear the darkness that had protected them. Crews whose morale remained high through the early war years grew demoralized by repeated surprise attacks they couldn't explain or defend against. Of the approximately 40,000 German sailors who served in U-boats during World War II, 30,000 died. The majority of those deaths came after mid-1943, when radar made surface operations, suicidal and submerged operations ineffective. The casualty rate, 75%, exceeded any other branch of any military service in the war. It reflected the brutal effectiveness of Allied anti-submarine warfare once technological advantages shifted decisively away from submarines. Admiral Dönitz himself acknowledged the role of Allied radar in his post-war memoirs. "The enemy's radar development had progressed far beyond our own," he wrote. "We were fighting with equipment designed for 1939 conditions against technology we couldn't match. The submarines became hunted rather than hunters. The night no longer offered protection. In the end, we simply couldn't win against such technological superiority." The civilian scientists who developed Type 271 radar received limited recognition during the war, as classified programs rarely generated public acknowledgement. But their contribution to Allied victory was as significant as any weapon system developed during the conflict. They had taken a laboratory curiosity, the cavity magnetron generating microwave frequencies, and transformed it into operational radar that worked reliably on small ships in the worst weather Earth offers. They had solved engineering problems that traditional military experts said were impossible, packaging sophisticated electronics into systems that exhausted sailors could maintain with basic tools. And they had created the weapon that made submarines visible in total darkness, ending the U-boat threat that came closest to defeating Britain before American industrial might could tip the balance. The irony was perfect and profound. The German naval tradition that produced the submarine tactics threatening Britain's survival couldn't match the innovation of British civilian scientists who'd never commanded warships. The radar operators who saved convoys were often teenagers trained in electronics for a few weeks, not career naval officers with decades of experience. The technology that won the Battle of the Atlantic came from laboratories and universities, not from arsenals and naval bases. World War II proved many things about modern warfare, but perhaps none more clearly than this: technology matters more than tradition. Innovation defeats experience, and sometimes the most dangerous weapon comes not from generals and admirals, but from scientists in laboratories who understand that the laws of physics don't care about centuries of naval doctrine. November 1945, Portsmouth, England. The war in Europe has been over for 6 months. HMS Marigold sits at the dockside, scheduled for decommissioning and scrapping. Her Type 271 radar, the equipment that detected U-433 in November 1941 and proved that microwave radar could kill submarines in total darkness, will be removed and sent to a museum or perhaps melted down for scrap metal. Petty Officer Thomas Brennan, the radar operator who trained hundreds of sailors in the technology that won the Battle of the Atlantic, takes one final look at the radar cabin where he spent so many watches scanning for submarines. The equipment that once seemed like magic now appears almost primitive. The cathode ray display with its glowing green screen, the manual steering wheel for rotating the antenna, the racks of vacuum tubes that required constant replacement. In 4 years, radar technology has advanced so far that the Type 271 looks like ancient history, already being replaced by more sophisticated systems with longer range and better discrimination. But this equipment did what it needed to do. It made submarines visible in darkness. It gave escorts the advantage in the night battle that threatened Britain's survival. It killed enough U-boats to turn the tide of the war. Brennan remembers the first contact, that November night in 1941, when the radar detected a submarine at 3,000 yards and guided Marigold through a perfect attack. He remembers the skepticism of officers who didn't trust electronic blips over visual observation. He remembers the equipment failures, the false contacts, the learning process that cost lives while crews figured out how to use technology nobody fully understood. And he remembers the moment, probably sometime in mid-1943, when radar stopped being experimental and became standard. When crews stopped questioning whether it worked and started depending on it. When submarine commanders stopped being surprised by night attacks and started being terrified of them, the technology had won, not through any single brilliant insight or dramatic moment, but through systematic application of physics to warfare. Radio waves bounce off steel hulls. If you can generate enough power at short enough wavelengths, and if you can detect the weak echoes returning to your antenna, you can see submarines in total darkness. Everything else, all the engineering and tactics and training, was just working out the details. Brennan closes the radar cabin door and walks down Marigold's gangway for the last time. Behind him, the corvette that proved radar could win wars sits silent at the dock, her service complete. Ahead, the post-war world where microwave technology will transform communications, cooking, medicine, and 100 other fields. But for 4 years, from 1941 to 1945, that technology had one purpose: make submarines visible, track them through darkness, kill them before they kill merchant sailors. And in that mission, Type 271 radar and the sailors who operated it achieved something historians would recognize as decisive. They won the Battle of the Atlantic. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.